Good morning, students. Hope you are all doing good and staying safe at home. So now we will start with an online session for your arrear to clear your arrears. So now we will start with the subject name electrical technology. So in our electrical technology, we are just going to discuss today about your unit 1, which is nothing but it's going to be your magnetic circuit. So now I have just displayed on the PPT what are the topics it's going to be discussed. So today in under your magnetic circuit, we are going to see the very important topics. First, we will have a glance of basic definition of magnetic circuits, then electromagnetic induction, Fleming's rule, Lenz's law, Faraday's law, induced EMF, statically and dynamically induced EMF, self-inductance and mutual inductance. And then we will finally have an analogous, that is nothing but comparison of electric and magnetic circuit. So this online class is being arranged for you people to make it very useful for you to clear your arrear paper. So now starting with your magnetic circuits, you know what you mean by a magnet. A magnet is nothing but, you can see the picture here on the screen. You can see I have an iron filling. I'm just spreading the iron filling and moving the magnet. So you can see more of my iron fillings to be deposited at the ends. And those ends, you call it as your poles. So here you can say you have more force of attraction at the poles. So hence, therefore, you can say the like poles repel each other and unlike poles attract each other. This is a very important property of a magnet. A magnet is nothing but it always has a magnetic lines of force traveling from your north pole to your south pole or south pole to your north pole. Hence, therefore, you have more force of attraction at the ends of the poles. So now here you can see the few definitions which have been highlighted here on the screen. What do you mean by a magnetic induction? A magnetic induction is nothing but when you are going to keep a magnet near your iron filling, you can see more number of iron fillings to be deposited at the ends. So this has been happening due to the phenomenon, and that phenomenon you call it as magnetic induction. Magnetic field. Magnetic field is nothing but you call it as the force surrounding a permanent magnet or a moving charge particle in which the another permanent magnet or a moving charge experience a force. So the force of attraction experience around your magnet, in short, you call it as a magnetic field. And this force of attraction, when it is going to exit, you have the lines of force traveling around your magnet, and that you call it as your magnetic lines of force. And what do you mean by magnetic flux? So flux is nothing but, I told you, around the magnet you have a force of attraction around your north pole and the south pole. Hence, therefore, the total number of lines that has been existing in a particular magnetic field is called as magnetic flux. So magnetic flux, it is being denoted by a unit called Weber. The symbol for magnetic flux is pi. So you can make this for all these definitions are very important for your 2-mark question in this particular magnetic circuits unit. Make a note of it. So 1 Weber, you can write it as 1 into 10 to the power of 8 lines of force. Similarly, what do you mean by magnetic flux density? It is nothing but the total number of magnetic lines of force passing through a specific area in a magnetic field, and it is denoted by a symbol B. So B is given by flux by A. So unit of flux is pi, area is denoted by meter square. Hence the magnetic flux unit is Weber per meter square, or otherwise, in other words, you can call it as Tesla. So make a note of this expression. This expression we will be using it in the further problems and all. So right. So magnetic flux is nothing but B is going to be equal to magnetic flux density is equal to flux divided by area given in terms of Weber per meter square or Tesla. Next is your magnetomotive force. So magnetomotive force is nothing but it is the cost for producing your magnetic flux in your magnetic circuit. So you can see the magnetomotive force completely depends upon the number of turns you have been having it on the coil and the current flowing through the coil. So it is given as N into I and its unit is ampere turns because the unit for number of turns is turns and current is measured in terms of ampere. Hence the magnetomotive force, the unit is given in terms of ampere turns. Next is nothing but the reluctance. The reluctance is nothing but the property similar to that of the property of resistance, what we have it in a magnetic circuit. So reluctance is nothing but you can define as the opposition that is going to be offered in your magnetic circuit to oppose your flux is called as your reluctance. So reluctance is denoted by a term called S and it is given by Ni. Ni is nothing but the magnetomotive force divided by your flux. Hence, therefore, its unit is ampere turns per Weber. And next is your permanence. A permanence is nothing but the reciprocal of your reluctance. You call it as permanence. Hence, it is denoted by a symbol P. P is equal to 1 by S and its unit is just the reverse of your reluctance, which is nothing but Weber per ampere turn. So reluctance is a very important property in your magnetic circuit. This is nothing but the opposition that is going to be offered in your magnetic circuit to oppose your magnetic flux set up in your magnetic circuit. So now next thing is your magnetic field strength. So magnetic field strength, it is denoted by, it is nothing but the force experienced by a unit end pole when it passes through any magnetic field. It is denoted by H. It has two units. One unit is according to the definition and the given expression ampere turn per meter, and the other physical unit it has is Newton per Weber. So the magnetic field strength H is equal to ampere turns per the length of the coil. So ampere turns is nothing but Ni. Ni is nothing but your magnetomotive force per length and its unit is ampere turns per meter, or otherwise you can call it as your Newton. Next is your permeability. Permeability is nothing but the ability with which the magnetic material forces the magnetic flux through a given medium. So the permeability always depends upon the conductivity of the magnetic material which is being produced on your magnetic material where you have your magnetic flux to be set up. So you can say my magnetic B is nothing but magnetic flux is directly proportional to your H. H is nothing but a magnetic field intensity. Right. So now I am going to remove this proportionality sign. Hence, therefore, I am introducing a constant called mu, and this is nothing but you call it as your permeability. So mu can be given as B is equal to B by H. So mu also can be defined as mu naught into mu r. Mu naught is nothing but the absolute permeability and mu r is nothing but the relative permeability of the magnetic material which is being used on your magnetic circuit. So these are the some of the very important definitions where you need to go through these definitions from which you will be getting your 2-mark question, or otherwise based on this definition you have your expression. For example, B is equal to magnetic flux is equal to pi by A. Then magnetic field strength H is equal to mmf by L. mmf is nothing but N into I. So these expressions, based on all these definitions, we are getting these expressions, formulas, which we will be using it on to solve your problem. So this is how you need to study for this initial part of your magnetic circuit, followed by a basic definition, followed by expression. So based on these expressions, we are going to see few problems. So few problems which have been highlighted in the PPT. These are the problems asked in your university for your university questions as well as for your assessment test. These same problems has been repeated, similar problems, right? So here listen to this problem. A bar of iron 1 centimeter square in cross section has 10 to the power of -4 where magnetic flux in it. Find its magnetic flux density of the bar if the relative permeability of the iron is 2000 and what is its magnetic field intensity. So here they've asked you to find your magnetic flux B, as well as they've asked you to find out the magnetic field intensity. So what's the formula for your magnetic flux? Magnetic flux density B is given by flux divided by a area. Similarly, what's the formula for your magnetic field intensity H? H is nothing but B by mu, and mu is nothing but the permeability, which can be written as mu naught into mu r. Mu naught is nothing but your absolute permeability, which always has a standard value of 4 pi into 10 to the power minus 7. And mu r is nothing but the relative permeability, and the relative permeability for air is always 1. Please remember, a relative permeability value for air is 1. But here in this problem, I have mentioned you the relative permeability of the iron to be 2000. Hence, therefore, mu r value is 2000. So they have given you the area of cross section of the iron bar is given as 1 centimeter square. You need to convert in terms of meter. So in terms centimeter square, in terms of meter square, it is 10 to the power of minus 4. Hence, therefore, the flux pi can be is given. Flux pi is given as again 10 to the power of minus 4 Weber, and the relative permeability is 2000. Now let us find out the magnetic flux density, which is given by flux by area. Flux is nothing but here, it's given there in the problem, 10 to the power of minus 4 divided by area. Area of the cross section, centimeter square, we are converting into meter square again, which is 1 into 10 to the power of minus 4. Hence the magnetic flux density B is given as 1 Weber per meter square. Similarly, the magnetic field strength H is the formula is given by B by mu. Mu is nothing but mu naught mu r. Mu naught is your absolute permeability, 4 pi into 10 power minus 7. And mu r is nothing but a relative permeability. The value here is given there as 2000. If the value is not given, then you can assume the mu r value for your air to be equal to 1. So take your mu r value as just 1 and you can substitute it, right? So now when I'm substituting, I'm getting 397.88. And please don't forget to mention your unit. Unit is very important. So it's nothing but ampere turns per meter. So this is the simple problems. So this type of simple problems you will be getting from the first half of your magnetic circuits, right? So the problems which has been discussed here on the slide are frequently asked problems for your university exam as well as even for your assessment test. So go through we'll move on to the next problem. In the next problem, you can see you have a mild steel ring of mean circumference 50 centimeter, and the cross section area is given as 5 centimeter square with the number of turns of 250 turns wound uniformly around it. So here you need to calculate its reluctance, and also you need to calculate the current that is required to produce the flux of 700 microweber in the ring. So now here they have given the relative permeability value of mild steel to be taken as 380. So now what's the formula for calculating your reluctance? Reluctance is nothing but the opposition produced to disturb your magnetic flux that is being set up on your magnetic circuit. You call it as your reluctance. Now for reluctance, we have two formulas. According to the definition, we have one formula. S is equal to Ni by L. That is, Ni is nothing but the magnetomotive force divided by here. But here you can see the values has been given in terms of the dimensions of the coil. Hence, in terms of the dimension of the coil, the reluctance is defined as L divided by mu naught mu r into A. Mu naught is the absolute permeability, which is always fixed, 4 pi into 10 power minus 7, and mu r value is nothing but the relative permeability of the mild steel, which has been mentioned in the problem as 380, and the area of the cross section of the iron ring is given as 5 centimeter square. So centimeter square, always you need to convert in terms of your meter square, which is nothing but 5 into 10 to the power of minus 4 meter square. So substitute the value, and the length of the iron ring I have mentioned here in the problem is 50 centimeter. Again converted in terms of meter square. So 50 into 10 power, convert in terms of meter. So it will be 50 into 10 power minus 2. Substituting this value, you are getting this final value as 2094,144. And please don't forget to write your unit. Your unit is ampere turns per Weber. Now how to calculate your current? Current I is nothing but you need to calculate your current. So you have another formula for reluctance. S is equal to Ni by L. number of turns has been given, and S value we know, and then L value we know, substituted, from which the current required for the magnetic flux of 700 micro and 700 microweber can be easily calculated. So this is the second model of the problem, right? So you can see this within these two problems. I have just covered what are the basic expressions we have it. Remember your magnetic flux density, then field, the magnetic field intensity, and remember your reluctance, and similarly remember your permeability. Mu is equal to mu naught into mu r. So these are based upon your definitions. All the final formulas, expressions I have given. When you are just preparing for an exam, please do write these expressions and have it in the mind, because from the half the of your magnetic circuit we will be using only these formulas from where you can get the problems. Okay, now we will go on to the next half of your magnetic circuit, which is going to be electromagnetism. Electromagnetism is nothing but, you can see, when I'm going to take a normal coil, for example, take a coil having an n number of turns, and to a coil, when the current is made to pass through the coil will have a magnetism property in it, right? So when the current flows through the coil, only when the current is flowing, you're going to have the magnetism property existing on the coil. And when the current is being removed from the coil, or the current is being stopped, you don't have the magnetism property to be existing. So this property of this property of electromagnetism existing on your magnetic material, in short, you call it as your electromagnetic material. So for a very good example for an electromagnetism or is going to be your induction stove, your transformers, your generator, your telephones, your microphones, your headphones, everything nowadays we have been just using an electromagnetic induction principle. So this electromagnetic induction principle was developed by a very great scientist, Michael Faraday, and he has been developed in the year 1831. So what has been happening over here is, whenever the flux linking with the coil is changing, you will be having the EMF to be induced in this coil. Please remember, this is the definition for your electromagnetic induction, which is very important even for your 2-mark question. What do you mean by an electromagnetic induction? It's a repeated 2-mark question, right? Whenever the magnetic flux linking with the coil is changing, an EMF is going to be induced in this coil, and this is called as electromagnetic induction. And this applications, also make a note of it for your 2-mark question. Applications is microphones, telephones, transformers, generators, motors, and then your headphones, induction stove, everything works on the principle of electromagnetic induction. So now I'm just going to explain you the electromagnetic induction by the simple diagram. That is how an EMF is going to be induced. An EMF is nothing but the electromotive force. When the EMF is induced, you can see the current starts flowing towards on your coil. How it is going to happen, you can see the diagram over here. I have taken a magnet, and to the magnet you can see this is a magnet with the north pole and the south pole. Let it be in the position A and B. On to the other side, what I've done it over here, I have taken a coil of n number of turns, and this coil is going to be kept on a magnetic material. The ends of the coil is going to be connected to the galvanometer. So now when the magnet is moved towards the coil, you can see the deflection on the galvanometer. Similarly, when the magnet is moved away from the coil, you can see the deflection on the galvanometer. But when the magnet is going to be kept stationary, you cannot see any deflection on the galvanometer. So whenever the magnet is moving towards the coil or away from the coil, the movement of the magnet makes you to show the deflection on your galvanometer. Hence, therefore, because why you are going to have this deflection on the galvanometer? Because according to your Faraday's law of electromagnetic induction, when you are moving the magnet towards the coil, the flux is changing in the coil. Similarly, when you are moving the magnet away from the coil, the flux is changing in the coil. So what I've said it over here, what do you mean by electromagnetic induction? Whenever the flux linking with the coil is changing, you are going to have an EMF to be produced. So EMF is nothing but your electromotive force. So this is how your EMF is going to be produced. So that's what I have given over there, the production of the induced EMF. I'm going to illustrate by three different methods. This is the first method. So when the magnet is moved towards the coil or away from the coil, you can see the deflection in the galvanometer, and the magnet remains stationary. You can see you don't have any deflection onto your galvanometer. So when the magnet is moved towards the coil or away from the coil, the flux linking with the coil is changes, and therefore you are going to have an electromagnetic force to be produced. So now this is your second method. Here you can see I've taken two coils. These two coils, you can see, you can remember this diagram you have already seen in your transformer. This is nothing but a transformer only, right? You have two coils which have been magnetically coupled with respect to each other, and I'm applying an input voltage of V1 of AC source is applied to the first coil. So when I am been applying a voltage to the first coil 1, what will happen over here? You will be having a flux of phi1 to be set up. So since both the coils have been magnetically coupled, whatever the flux that is being set up here in the coil 1 will be linking with the coil 2. Hence, therefore, you have another flux of phi2 to be set up. So as the input voltage is varied, the flux linking with the coil 1 is changing, which will automatically change the flux linking with the coil 2. Hence, you can see the deflection on the galvanometer. So this is a very good example, and this example is nothing but it's going to be given by your, it's going to be the simple operation of your transformer. So from this, what I want to say it over here is I wanted to explain the phenomenon of electromagnetic induction. What has been happening in your electromagnetic induction principle? So now this electromagnetic induction principle, this scientist Faraday, he has given us two laws. Make a note of this Faraday's law. You can explain the Faraday's law of electromagnetic induction. It can be a 12-mark question or it can be an 8-mark question. See to it the marks that is being allotted for your particular question. Depending upon the weightage of the mark, you please answer to your question, right? So the first law and second law, it's also very important even for your 2 marks also. So what first law is saying is, whenever the conductor cuts the magnetic field, an EMF is induced, or otherwise whenever the magnetic flux linking with the coil is changes, an EMF is induced. So of this Faraday's law only, I have just shown it as an illustration in your method 1 and method 2. And from your Faraday's second law, we are going to get an expression that is nothing but E is equal to N into d phi by dt. How I'm getting this expression, that explanation I have shown it here on the screen. So according to your second law, the magnitude of the induced EMF is equal to the rate of change of the flux linkage. So initially you will be having a flux linkage of N into phi, and N is always, remember, the number of turns on your magnetic coil. The final flux linkage can be N into pi 2. So what will be a change of flux linkage? It is nothing but N into pi 2 minus your pi 1 pi, that is final value minus your initial value. So the rate of change of flux means with respect to your time. So you can write it as N into pi 2 minus pi 1 divided by T. So let E be the EMF induced according to your Faraday's law, and E is equal to N into d phi by dt. What is your d phi? D phi is nothing but your change in flux. So you can see the your EMF which is going to be induced, it is not meant that always you will be having a positive EMF. You will also have sometimes negative EMF. It depends upon the change of the flux what you're going to get it, right? So you can see when the direction of the induced EMF is so as going to be the opposite, the very cause producing it, it is going to be given by a negative sign as E is equal to minus N into d phi by dt. So please remember this expression. Based on this expression, we will be solving few problems also, right? So now I told you the electromagnetic induction principle. So in that electromagnetic induction principle, we are going to get an induced EMF. Now how to obtain the direction of the induced EMF is given by 3 basic rules. First thing is your Clemens Rectangle rule. and Fleming's right hand rule, and then your Lenz law. So the direction of induced EMF can be obtained by using Fleming's right hand, left hand, and your Lenz law. So what is your Fleming's right hand? So Fleming's right hand rule, Fleming's left hand rule, Lenz law is very important for your 2-mark question. Or otherwise, the direction of induced EMF can be totally summarized and asked for your 6 marks or for 8 marks. Make a note of it, students. So statement given over here for your Fleming's right hand rule, very simple. Take your right hand, stretch your forefinger, middle finger and thumb such that they have been mutually perpendicular to respect to your each others. Remember, please remember this diagram so that you won't forget it at all. Forefinger always denotes the direction of magnetic field, middle finger denotes your direction of current, and thumb denotes the direction of the motion of the conductor. Similarly, a Fleming's left hand rule means you have to take your left hand and stretch your forefinger, middle finger and thumb such that they have been right angles to respect to each other. So here the forefinger is going to denote your magnetic field, middle finger denotes the direction of current, and thumb indicates the direction of the mechanical force that is going to be exerted onto your conductor. The next thing is your Lenz law. Lenz law is nothing but very simple. I've showed you in the previous thing, that is E is equal to minus N into d phi by dt. That is, when you're going to get your d phi value to be as negative, then the direction of the induced EMF is going to be given by a Lenz law. Lenz law is a very important 2-mark question. Make a note of it. What do you mean by a Lenz law? So Lenz law is nothing but the direction of the induced EMF is going to be so as the very cause producing it, and it is given by E is equal to minus N into d phi by dt. So the direction of the induced EMF is given by your Fleming's left hand rule, Fleming's right hand rule, and Lenz law. So this direction of induced EMF, this particular topic, prepare for your 6 marks or 8 marks, or definitely or otherwise you will be getting at least 2 marks from this topic, right? Now going on to the types of induced EMF. You have 2 types of induced EMF. So first I started with the electromagnetic induction principle, and then I explained you how the electromagnetism induction principle is obtained by your 2 methods I explained you. Next I have explained you the induced EMF expression given by your Faraday's law, Faraday's first law and first law I explained you, and then how to find out the direction of the induced EMF I explained you by using a Fleming's left hand rule, right hand rule and Lenz law. Next we are going to study about the types of the induced EMF. We are going to have 2 types of the induced EMF. One is your dynamically induced EMF and the other one is just statically induced EMF. Dynamic means what? Generally you say dynamic means it is going to be in motion. So dynamically induced EMF is nothing but the EMF that is going to be obtained when the magnetic field or a conductor is going to be rotating in nature. And the other case we have it is statically induced EMF. Statically means what? Stationary. In that case, what you're going to say, both your magnetic field as well as your conductor, both is going to be kept stationary for you. So now first let us discuss about the dynamically induced EMF. So this dynamically induced EMF, the types of induced EMF, they can ask you for your 16-mark question, or otherwise they will mention separately. Explain the dynamically induced EMF and obtain this expression. As this can be asked as A part, and B part they can ask you as your problems. Okay, and so therefore for a dynamically induced EMF, what is the expression we are going to get it, and that expression we can use it, we will be implementing here in our problem. Okay, so dynamically induced EMF, dynamics means in motion. Please remember that when a conductor, so you can see the diagram over here. I have taken and bar magnets, North Pole and South Pole. So between the magnets, you're going to have a magnetic field. Now in the magnetic field, I'm going to keep a conductor. Now this conductor is going to be kept stationary. And initially when it is going to be kept stationary, you're not going to have any magnetic, you don't have any electromagnetic induction principle to be obtained. That is, you don't have any EMF to be obtained. Now the same conductor, it is going to be moved with the velocity of v. So when the conductor is moved in the velocity of v, you can see it when the conductor is moving, it will cut the magnetic lines of force. So according to your Faraday's law, what do you mean by that? When the conductor cuts the magnetic lines of force, you will be having an EMF to be obtained. So here you can see I have a uniform magnetic field. On a uniform magnetic field, the conductor is going to be moved with the velocity of v. So when the conductor is being moved with the velocity of v, you can see a magnetic an electromagnetic induction principle to be obtained. So when the conductor is cutting the magnetic field, what will happen? The flux linking with the coil will be changing. When the flux linking with the coil on the magnetic field is changing, definitely you will be having an electromotive force, which is nothing but the EMF to be obtained. So now, for example, if the conductor is going to be moved with an angle, making an angle of theta. So this is going to be exactly at right angle, right? So if I'm going to move the conductor this way, you're going to take it as V sine theta. And if I'm going to move the conductor with an angle towards downwards, you can take it as V cos theta. You can see the phasor diagram which I've been shown it over here. So now if the conductor is going to move cross-sectionally or diagonally making an angle theta, you will be getting an expression accordingly. Now see here, when the conductor, according to your Faraday's law of electromagnetic induction, the EMF induced E is equal to N into d phi by dt. Here we are going to take the conductor which is going to have the number of turns to be N is equal to 1. So E is equal to what I can write, d phi by dt. D phi is nothing but what? I can write it as the change in the flux. When you are going to have the change in the flux, when the conductor is moving. So when the conductor is moving on a uniform magnetic field, which is given by your magnetic flux B into the length of your magnetic lines of force into your dx. So dx is nothing but you can see the how long the distance, the magnetic, how long in the distance of your magnetic field it has been moved. So the electromagnetic induction E is equal to given as BLV in terms of your volt. So V is nothing but your linear velocity, which can be given as dx by dt. So now if it is going to move with an angle of theta, so for an angle of theta, what you will be getting an expression, electromagnetic induction, the EMF induced E is equal to BLV sine theta. So please remember this expression. For a dynamically induced EMF, E is equal to BLV in terms of volt. And if the conductor is making an angle of theta, then you can write it as BLV in terms of theta is nothing but we are going to write it in terms of sine theta. And don't forget this unit. The unit for a EMF is always going to be volt. So this is for your dynamics. So here what has been happening? When the conductor is moving on a uniform magnetic field, you are going to have a electromotive force or EMF to be obtained. So here you can say your conductor is going to be in motion. The conductor is moving on a uniform magnetic field. Hence, therefore, this type of EMF induced, you call it as your dynamically induced. So when your EMF is induced, only when the conductor is moving. So the conductor, since the conductor is going to be in motion, you call this type of EMF as a dynamically induced EMF. So next we are going to see is going to be your next type, which is nothing but your statically induced EMF. So statically induced EMF is nothing but both your conductor as well as your magnet, both is going to be kept stationary. So here you can see I have taken a an uniform iron rod, and on a uniform iron rod I have kept a coil of n number of turns connected to it. So now if the current of I is been applied, what happens? I will be having the magnetic flux to be linked on the coil. So that is what given in your Faraday's first law. Whenever the magnetic flux linking with the coil is changing, the EMF is going to be induced. And this EMF, you call it as what? Statically induced EMF. So here in this case, you can see your coil is not moving and you're not even moving your magnetic circuit. Nothing is going to be moving over there. Everything is kept stationary. Just you're going to change the current flowing through the coil. So when the current flowing through the coil is changing, Then N5, magnetic flux linking with the coil is changing. When the magnetic flux linking with the coil is changing, you're going to have your statically induced EMF to be produced. Your statically induced EMF is again further being classified into two. One is your self-induced EMF and the other one is your mutual induced EMF. So self means what? By ourselves. So you can see it. The flux is going, I'm taking only one iron ring. Onto this one iron ring, a coil of n number of turns, I have been kept it over there. So the coil for this coil of this n number of turns, you can see it over here. I have only one iron ring with a coil of n number of turns. So here you can say that this n number of turns, as the current flowing through the coil is changing, the flux linking with the coil is changing. So because of that, you have the EMF to be produced. So everything is taking place within the same coil, and this type of EMF, you call it as self-induced EMF. While the other thing, when I'm going to refer it and see it over here, you have two coils. That is, I've taken the two iron rings and the two coils to be connected over there. One, you have been by varying a rheostat through a battery source, you are going to vary the current flowing through it. So when I'm going to vary the rheostat, the current flowing through the coil B is changing. And when the current flowing through the coil B is changing, the flux linked with this coil will be linking with the coil A. Hence, the current flowing in the nearby coil A also will be changing. So here you can say mutually my coil A and coil B are mutually coupled. Okay. So when the current flowing through the one coil is changing, the EMF linking with the second coil is also been changing. So this type of sharing taking place between two coils and the EMF induced by this type, you call it as your mutually induced EMF. So statically induced EMF means the EMF that is going to be induced without any movement of your coil, and therefore you can see this type of EMF, you call it a statically induced EMF. When you will have the statically induced EMF to be obtained is when the flux linking with the coil is changes, the EMF is going to be obtained according to your Faraday's first law of electromagnetic induction. Under that, you are going to have two types, self-induced and mutual induced. Self-induced means the current flowing in the first coil and the flux linkage taking place on the same coil. And mutually induced means the current flowing in the first coil will be changing, and the flux, because of the current flowing the first coil is changing, the flux linkage will be changing in the next coil, the nearby coil. So it is being mutually sharing, you have a mutual sharing of the induced EMF between both the coil, that you call it as your mutually induced EMF, right? So because of this self-induced EMF and mutually induced EMF, you are going to see the expression for the self-inductance. So in the expression for the self-inductance is given by Faraday's law, which we have been already studied. E is equal to N into d phi by dt. Now when I'm going to talk about the self-induced EMF, for each and every coil of this induced EMF on the coil, it has an inductance property on it. So the inductance property which is going to be existing on a self-induced coil, you call it as the self-inductance of the coil. So the self-inductance of the coil is given by the property of the coil that opposes any change of the amount of the current flowing through it. So remember, it depends upon the shape of the coil and the number of turns. It depends upon the relative permeability, and it also depends upon the speed in which the magnetic flux is being changing. So you know that my self-induced EMF E is given by N into d phi by dt. Okay. So now since the flux depends upon the current, what I can say, this pi, I can send it as N into pi. N pi is nothing but what? N is your number of turns and pi is your flux. So when you are going to have the flux linkage, when the flux linkage, when it is going to be obtained, when the current flowing through the coil is changing, you will be having a flux linkage. Hence, therefore, I can say N pi is directly proportional to I. So from this, I can say E is directly proportional to di by dt. So comparing this first expression and second expression, I can write E is equal to L into di by dt, and this L is nothing but you call it as the self-inductance of the coil. So the self-inductance of the coil, other expressions, everything we have it. Please make a note of all these expressions, because the second half of the magnetic circuit, the problems will be focused on your electromagnetic induction principle. That is, first thing, expression E is equal to N into d phi by dt. That is default Faraday's law. Next, the expressions what you're going to see it under your self-induced EMF, mutual induced EMF, self-inductance and mutual inductance. Based on these parts, we will be having the problematic sessions on it, right? So from this method 1, you know E is nothing but L into di by dt. So I can write it as di by dt into Li. And E is, according to Faraday's law, E is equal to N into d phi by dt. Now comparing 1 and 2, what I can write? D phi by dt, I can write it as Li is equal to N into pi, from which the self-inductance of the coil L is equal to N phi by I. So first expression we have got it, E is equal to L into di by dt. Next expression, L is equal to N phi by I. N into phi is nothing but the flux linking with the coil. Okay. And then the second thing is in terms of the dimensions of the coil. In terms of dimensions of the coil, you know that the reluctance S is equal to L divided by your mu naught mu R into A. So in that case, you can write it as what is your B? B is equal to mu naught mu R into H. H is nothing but what? We have studied magnetic field strength, which is Ni by L. And what is your flux pi? Pi is nothing but flux density into A. So you just substituted mu naught mu R Ni by L into my A will give me my flux pi. So let me calculate my flux linkage N phi. How I will be getting it over here? Already I have an N term, so it changes to N square into I into mu naught mu R A divided by my L. And what is my L from the previous expression? It is N phi by I. So substitute it over here. So finally you are going to get the inductance of the self-inductance of the coil in terms of this dimensions of the coil. That is N square divided by S. S is nothing but the reluctance of your magnetic material, which is given by L divided by your mu naught mu R into A. So we have got three expressions based on your self-inductance. First, based upon the change in the current with respect to time, E is equal to L into di by dt. Now change depending upon the flux linkage, L is given by N pi by I. And based upon the dimensions of the coil, L is given as N square by S. S is nothing but the reluctance of your coil. Similarly, the same way we are going to see it for your mutually induced EMF. So already I told you, what do you mean by mutually induced EMF? When the current flowing through the coil 1, for example, coil X is changing, the flux linking with the coil Y will be changing because of the principle of your mutual inductance, right? So you're going to see the mutual inductance property. So the mutual EMF in the coil Y is directly proportional to the rate of change of the current in your coil X. So my mutually induced EMF EM is given by M into di1 divided by dt. That is the mutual induced, the current is changing in the first coil, but the EMF is going to be induced onto your nearby coil, and the property which is going to have the existence of mutually induced EMF, that property of the coil, you call it as your mutual inductance of the coil. So first expression based upon EMF induced, EM is equal to M into di by dt. M is nothing but the mutual inductance of the coil. The second expression, we are going to get it based upon your magnetical, that is based upon your coefficient of your coupling. So remember this expression, E is equal to M into di by dt. Di by dt nothing but when the current flowing in the first coil is changing, the EMF is going to be obtained onto the nearby coil. So now based upon the mutual inductance property and the self-inductance property, we are going to study the coefficient of coupling. So make a note of it. Coefficient of coupling is very important. They can ask you this derivation unknown separately. So for the coefficient of coupling, you can see the diagram. This diagram, the same diagram what I have been given for you in the mutual induced EMF explanation, the same diagram I have taken it over here. So V1 is going to be the input applied. This is your coil 1, coil 2. When the V1 is applied, current, the flux of phi1 will be set up in your coil 1. And since both the coils have been magnetically coupled, the flux phi1 linking with the second coil and the flux of phi2 will be obtained. So the mutual flux obtained between both the coil 1 and coil 2 is given by pi1 2. So now here you can see my coefficient of coupling can be Km given by pi1 2. Pi1 2 is nothing but what? The flux linking with both the coils, coil 1 and coil 2, which can be written as K into pi1. Pi1 is the EMF flux that is going to obtain only on your coil 1. Similarly, the reciprocal wise, I can say K is also equal to pi 1 divided by pi 2. Pi 1 is nothing but K times of my pi 1. So let me know that the mutual induced EMF, I have derived it, M is equal to N2 pi 2 divided by my I1. So what is your, similarly, in terms of second coil, with respect to second coil, you can write it as N1 pi 1 divided by I2. So let me take the mutual inductance with respect to my coil 1 and coil 2, which I can write it as M square. So I'm going to write it. I'm getting it as N1, N2, N1, pi 1, 2, pi 2, 1 divided by my I1 into my I2. So what is your pi 1, 2 and pi 2, 1? I have showed you in equation number 1 and 2. So just take the values and substitute over here in terms of your coefficient of coupling K, and take the K term outside. So you will be getting N2 phi 2 by I2. N2 phi 2 by I2 is nothing but what? It is your L2. Similarly, N1 phi 1 by I1 is nothing but what? It's your L1. So from which K square is M square by L1 into L2. So coefficient of coupling K is given in terms of the mutual inductance of the coil and the self-inductance of the coil. So K is equal to M divided by square root of L1 into L2. So the derivation for your coefficient of coupling is important. It can be asked for your 12-mark question. So now, based upon it, you can see this question, analogy of magnetic and electric circuit, or otherwise they can ask you as similarities and dissimilarities between magnetic and electrical circuit. Several times it has been asked in a university question paper. Make a note of it. This is a very important question. They can ask you directly for 16 marks or for 12 marks. 16 marks, if the question has been asked, please write minimum of 15 points over here. Okay, so I have just highlighted 14 points onto my PPT here. So all this thing, everything we have already shared you in the course material. You can even refer to the course material for the further classification, for the further clarifications. Okay, so magnetic circuit and electric circuit, if they are going to ask you the similarities and dissimilarities or analogues of magnetic and electric circuits, whatever it might be, both the questions are same. So now we are going to have the comparison between magnetic circuit and electric circuit. So magnetic circuit, what will have, we will be having closed path for the magnetic flux to be set up. So magnetic flux will be set up, but in the case of electric current, when you are going to have the closed path, electric current starts flowing through it. So here flux is denoted by pi in terms of power, but here it is electric current I in terms of ampere. And you have the MMF, which is magnetomotive force N into I. But in electric circuits, you have your EMF, electromotive force in terms of your ohm. And your magnetic flux pi is MMF by reluctance. And here electric current I is EMF by resistance. So this is your Ohm's law of your magnetic circuit. That is also very important 2-mark question. State the Ohm's law of magnetic circuit mean, which is nothing but pi is equal to MMF divided by your reluctance. Okay. So reluctance S is nothing but L divided by mu naught mu R into A. And here it is given as resistance R is equal to rho L by A. And here reluctance, opposite of reluctance is permanence, and the opposite of resistance here is conductance. And here if it is going to have relativity, here in electric circuit it is going to be resistivity. And here it is permeability, means here there in the case of electric circuit it is conductivity. And in the case of magnetic circuit you have flux density. In case of electric circuit you have electric density. Please write all the expressions, everything. And here in this thing, your magnetic intense field intensity means here you can call it as your electric intensity. So what's the main difference over there? Magnetic flux is set up, it does not flows. So these up to the 10 points, you can write it as similarities. Okay, so from serial number 1 to serial number 10, it shows the similarities of your electric and magnetic circuit. Now from serial number 11 to serial number 14, it shows the dissimilarities between your electric and magnetic circuit. So what are the dissimilarities? You have it over here is magnetic flux is being is nice just set up, but here electric current starts flowing through it, and the reluctance of magnetic circuit is not constant, but here your resistance of the circuit will be partially constant, and here you can see your energy is being recovered to create the flux, but here the energy is recovered so long as the currents is being flowing in the circuit. And for the magnetic flux, we don't have any perfect insulators, but here for electric circuit, we have electrical insulators like glass, rubber, air, etc. So these 14 points are very important. Please by heart all these 14 points, which will be a very important part, that is a comparison or similarities and dissimilarities or on analogous of electric and magnetic circuit. Now we will move on to the problem based upon your electromagnetic induction. What are the problems which have been shown here on the PPT are the problems which have been asked for your university exam. So in the magnetic circuit, how it will be is, A part you can get it as a theoretical. For example, they can tell you that is derive, explain the dynamically induced EMF, or explain or deduct an expression for a magnetically induced EMF and the magnetic inductance of the coil, or otherwise they can ask you explain the coefficient of coupling or derive the coefficient of coupling. So remember, in your magnetic circuit, 95% A part you can get it as theory, and remaining B part you definitely will be having the problem. So please don't neglect the problems. Problems are very easy. If you remember the final expressions, all these definitions, everything, what you do it over here is, for this unit 1, you try to summarize and write it. What are the expressions we have it? Hardly we have around 7 to 8 expressions only, right? So those expressions, if you remember, you can easily solve the problems based upon your magnetic circuit. Definitely you'll be having the confidence to attend the problem. When the problem is given, don't get tense. Just go through the problem once or twice or thrice, and definitely just think what is the solution, how we can derive the solution, what can be the formula which can be used it over, what is the unknown parameter they've asked you to find it. So think twice, thrice, and definitely you'll be getting through the problem. Okay, so see to it what I have been asked it over here. Very simple question only they have asked it. Calculate the EMF induced in a coil of 200 turns when the flux linking with the coil is changing from 1 milliweber to 3 milliweber, and the time period is also been given for you. So they have asked you to calculate the EMF induced. So what is the EMF induced formula according to the Faradays law? E is equal to N into d phi by dt. Okay, and d phi is nothing but change in flux, and dt is nothing but the change in time. How to find out the change in flux? Final flux minus the initial flux. What's your final flux? It's changing from 1 milliweber, it's the initial value, to the final value. So final value is 3. So milliwebers, when they are giving this is the part where you people are making a mistake. Milliweber into 10 power 3, you're just neglecting. So please see to the what is the expressions or the units given over there, milli or micro or whatever it might be. Based on it, you substitute the value over here. So I'm getting it as 2 into 10 power minus 3 Weber, which is nothing but 2 milliweber. I got it. Now substituted to the E is equal to N value, number of turns is given as 200, and time change of flux is 2 into 10 power minus 3 with respect to your time dt. Now here you can see why I have given it as negative. What they have given over here, the flux linking with the coil is changing within the change of the time to be given as 0.1 second. So here you can see, if you are going to take it as positive or negative, nothing wrong in that. Both is going to be taken as the same value only. So E is, we have two expressions. E is equal to N into d phi by dt, and depending upon the change of flux to be more value, you can write the E is equal to minus N into d phi by dt. Anyhow, when I'm going to take my EMF, I'll be taking my magnitude in terms of positive value. So time I have given is 0.1 second, substitute it. So you're going to get the value as 4 volts. Okay. So this problem is very important. Simple problem based upon your electromagnetic induction. The next problem you can see same electromagnetic for fully in the electromagnetic induction type, then that problem definitely will be using mostly your Faraday's law. So remember this expression E is equal to N into d phi by dt. Okay, so here I have given number of turns, reluctance, current flowing through the coil, and then the time that is being required to reverse your current in terms of 10 milliseconds. Okay, so the EMF induced E is equal to N into d phi by dt. Okay, so what is your flux pi? Pi is nothing but mmf by s, N by s. So from this calculate your flux. After calculating your flux, they have given you within this time it has been reverse. So reverse means you're going to take it as your negative of value. So change in flux will be additivity, which is going to be 0.1 milliweber. So substitute it and the change in time is given, substitute it and get the values of expressions. Here we are using two formulas. E is equal to N into d phi by dt and flux pi is equal to mmf by S. Similarly, see the next problem based upon your self-inductance. Self-inductance expression is what? N phi by I. N value I have given, phi value I have given, I value I have given. Just take and substitute it in this particular problem. So only one thing, when the problem is given, first write the given data. What are the data is given for you, and then you write test to find what you need to find it, you write it. So from the given data and what is the thing you have to find it, correlate it, and for this correlation use your formulas. Very simple. So when you remember your final expressions of these formulas, you can easily substitute your formula and get the answer. So here, you know, L is equal to N square by S, right? S is nothing but what? L by mu naught mu R into S. Substitute these values and get this inductance, self-inductance in terms of your dimensions of the coil, right? So these are the few problems. These all the problems what I've showed you in the PPT are all taken from your university question bank. I have taken these problems and I have solved for you. And few important questions I have highlighted on the screen. Make a note of it. These are the repeated 2-mark questions which has been asked in your unit 1 part A, and similar 21 questions I have highlighted, and similarly part B also what are the important questions, and these questions what I have been given are the questions which have been taken from your university question paper. So these questions here, state the Faraday's law of electromagnetic induction and derive the expression for dynamically induced EMF. And second part question you see, explain the statically induced EMF with a neat diagram. And then the third question you see, what I've asked you to find out, I asked you to find out flux density. Flux density B is nothing but what? Pi by A. So flux is given, A is given, A is nothing but the area of cross section, everything is given. You can calculate it. MMF. MMF is nothing but what? See the next problem. N into I, number of turns into current. Reluctance is given by two formula. S is equal to Ni by L, one formula. And other thing, S is equal to L by mu naught mu R into A. How to calculate your flux pi? Pi can be given as B into A. Flux density B is nothing but what? Pi by A. So very simple. The problems based upon your magnetic circuits are very simple. You can easily get full marks from this particular unit magnetic circuit. Okay. So very simple questions only you'll be getting. See the comparing electric and magnetic circuit, very important. Please do study. And then coefficient of coupling K, how to find out? M divided by square root of L1 into L2. L1 and L2 is nothing but what? The self-inductance of the first coil and second coil. L1 how you can find out? N phi by I1. And L2 how you can find out? N phi by I2. Okay. Similarly, see this average induced EMF means what you mean by that? E is equal to N into d phi by dt. Okay. So these are all the important questions which I have been highlighted for you for your unit 1. Now moving on to your unit 5, these topics are very important for your unit 5. Please don't neglect it. Principle of operation of your alternator, and then stepper motor and servo motor. So alternator is nothing but it's going to be an AC generator. Generator means what it is going to do? It is going to convert your mechanical energy into your electrical energy. So two important parts of your alternator is your stator and rotor. Stator, you can see it on the screen. It is a stationary part of the machine which has all slots and windings to be kept in, right? And then rotor is the rotating part. On to your rotor, here you have two types. One is a Salign pole rotor and other one is cylindrical rotor. Salign pole rotor means you have like this projection of poles and on to which you are going to keep your rotor winding. But cylindrical means on your rotor itself you have the slots to be cut, and on to the slots you will be keeping your rotor winding. Okay, so what is the principle of the alternator? Very simple. You have two important parts, stator and the rotor. I said the rotor is the rotating part and stator is the stationary part. So first initially you are going to apply a small magnetic field to magnetize your stator. So once when the stator windings is being magnetized, what happens over there when you're going to make your rotor to rotate? On your rotor also you have the slots to be cut and you have all the conductors to be kept it on the rotor. Okay, so when this rotor conductors is going to cut your stationary magnetic field, you are going to have the EMF to be induced, and that EMF induced is going to be your AC electrical output, which you call it as your operation of your AC generator. Okay, next thing we are going to see is stepper motor. Stepper motor is a special machine which is very important. Where you are using a stepper motor in all the robotic applications, you are going to use your stepper motor. Robots, how it is going to move in terms of steps. So the motors used in your robots is going to be a stepper motor. So how we are going to move it is based upon the step angle. How to calculate the step angle? Which is given by 360 divided by m into nr. M is nothing but the number of stator slots and n is nothing but number of rotor slots. And here also in your stepper motor you have two important parts. One is the stator and another one is the rotor. So nr and ns is going to denote the number of the stator and the rotor tail. So stepper motor, we have three types of stepper motor: variable reluctance motor, permanent magnet motor and hybrid motor. So now we will discuss all these stepper motors. Are very types are very important. So the operation is more or less same with respect to all the three types. Now let me explain the variable reluctance motor. So variable reluctance motor is based upon the principle of your property of your magnetic flux line. So here you can see this is your outer ring is your stator and the inner ring is your rotor. Onto the rotor you have the slots to be cut, and onto the slots what you're going to keep it? You're going to keep your coil. Now you can see the coils A dash, B dash, C dash with respect to the switch. For example, see to this truth table. When my rotor is being rotating, you can see it is rotating in terms of steps. So you can vary your steps. How you can vary your step? You can vary your steps in terms of your step angle. Full rotation or a half rotation. So based upon your step angle measurement, you can vary it. Okay. Next is your servo motor. Servo motor is very simple. What you have studied with respect to your DC motor, you might have already studied. DC motor, in that motor, we have two important parts: field and armature. So when you're going to make your motor to be operated in a closed loop, you call it as your servo motor. So DC servo motor, you have your field control, and AC servo motor, you have your armature control. Okay, so these are the very important thing. And the next thing, AC servo motor also have given, and the partly important questions for your unit 5.